Good morning, teenagers. This is Mr. Williams. I am making this video for you because I will be absent on August 26th, 2019. I am aware that the video quality and sound may not be the best, but since my rank in League of Legends is somewhere around Plastic 4, I think it's unlikely that I will ever make the transition to a pro Twitch streamer. So you're just going to have to deal with this. However, the good news is I don't think that physics has changed much on these topics in the last several hundred years. So even though my video production quality may be archaic, I don't think that the physics is. Today, we are going to be talking and exploring more deeply something we talked about the other day. So we talked about the definition for distance, the definition for displacement, and the definition for the magnitude of the displacement. I recommend you look in your notes and remind yourself of what those terms mean. Also, we learned the definitions for the words scalars and vectors. So you might want to look at those words as well before we move on. I hope you took good notes. So let's explore together today these 5 words. We are going to look at a number of examples together. I'm going to try to work through them, and I hope that these examples I work through will help you understand these terms better. Before we get started, here's some big ideas I want to emphasize to you. I've not made a big point of them so far, but I want them to be stated clearly to you now. It would be my expectation that you would copy these down in your notebook as notes today. And in fact, I would expect that you would copy down everything we're doing here, so you can have it to study at home. The big idea number 1 today is you need to always draw a picture when you are thinking about a physical situation. We're going to be doing lots of complicated things in this class, but we're not going to jump in and do crazy complicated things at first. We're going to start out simple and get more complicated. But as we deal with complicated physical situations, it's going to be almost impossible to keep all the details in your head, and you're certainly not going to be able to think clearly or well if you try to do everything in your head. So you can't try to be a hero here and just figure it out with the amazing powers of your mind. You need to use paper and pencil, just like humans have been doing for a long time. You need to draw pictures. I'm going to outline some things I want on your pictures here in a minute, but in all my years doing this, kids, they just are resistant to drawing pictures. When I look at your tests, I got to say that the failure to draw a picture leads to more problems than any other single mistake. Please get in the habit, starting now, of always drawing a picture when reasoning about a physical situation. All right, let's move on to big idea number 2. When you draw a picture, you need to orient the picture to the reader. You need to clearly show which directions are positive and which are negative. Now, you have a choice about what is positive and negative. Is up going to be positive, or is it going to be negative? There's no right answer there. Sometimes it will make your problem easier to have up be negative. Not all the time, but sometimes. When you make that choice, you need to remind yourself by writing it in the picture, and you also need to inform anyone else who looks at the picture. Big idea number 3. You need to always clearly identify your origin in the picture. We're going to be doing complicated problems sometimes that have 2 or 3 steps in them. And it is fairly common for students to start out with the origin in one place in step number 1. Then in step number 2, they're like, oh, this would be so much easier if the origin got moved. And then in their head, they move the origin to make the next part easier. But they don't, they forget that they moved the origin. And then it causes all kinds of problems. They mess up, they get the wrong answer, and they're like, oh, what happened? Well, you didn't draw your origin in the first place, and then you didn't stick with your origin. You just shifted your origin around. You need to always clearly identify where your origin is in your picture. Big idea number 4, negative numbers. Oh, my Lord. You'd think they were easy. You probably learned about them in, second, third grade, or maybe even kindergarten, I don't know. But wherever you learn about negative numbers, they're going to cause trouble in physics because negatives have physical meaning in our discipline. A negative number means, for displacement, means that you are traveling backwards. Well, Mr. Williams, what direction is backwards? That, young person, depends on how you defined your directions up in big idea number 2. So that's why this is so important. Once you've identified which direction is positive and which is negative, then a negative number for displacement means you're going to go in the opposite direction of your positives. All right, let's move on. I made up a little example before I started this video, so I'm going to work through it with you. So Johnny starts 6 meters to the west of the origin. He then travels -4 meters. When he reaches his final destination, what is his distance traveled, his displacement from where he started, the magnitude of his displacement from where he started, his displacement from the origin, and the magnitude of his displacement from the origin. Okay, so we have 5 things we need to find here because I'm a wicked, evil man. So let's work through it together. First thing I should do is draw a picture. So I'm going to put my origin right here. And I'll keep it normal, kind of standard. In general, in most maps and stuff, to the right is going to be to the east. So I'll make it to the east here. So if to the east is positive, and this is the origin, let's see, I hope you can see that. I'm not sure about this camera. I don't know. Okay, whatever. So you start here at the origin, and you're going to go 6 meters to the west for him to start. 1, 2, 3, 4, 5, 6. So good old Johnny starts here. That's his start point. He travels 4 meters. 1, 2, 4. I'm just going to give you this to be sure that if you're going to get confused, you do it. Which direction does Johnny go? Hopefully you discussed it with your neighbors. Okay, if he's going -4, well, which direction is negative here? If this is positive, then he's going to go 4 this way. 1, 2, 3, 4. So then this is his ending point. The first thing I need to find is his distance traveled. Now, distance traveled is a scalar because there's only one piece of information there, just how far you go. The symbol I'm going to use is D with a subscript TRAV for travel. And the distance Johnny traveled is 1, 2, 3, 4. He went 4 meters. I'm going to put a box around it because I got that one. And I am going to cross this part of my question out. What is Johnny's displacement from where he traveled? So, from where he started. So he started here. His displacement would be in a straight line from where he started to where he ended. How far did he go and what direction did he go in? The symbol I'm going to use for that is d subscript travel. There's a symbol we use in physics for vectors that's basically half of an arrow. So I draw a straight line above my d, and then I make half of an arrowhead here. If I were to draw another little line right here, it would be a full arrowhead going backwards, but I'm not going to draw the bottom part. I'm just going to draw the top part. And so that means that this is the displacement. So this is the distance traveled. This is going to be the displacement traveled. That's the symbol I'm going to use for it. And the displacement traveled is going to be, well, there's two ways I could write it, really. I could say negative 4 meters, or I could say the displacement traveled is equal to 4 meters west. Either one of those would be the right answer. Well, Mr. Williams, which one is the real right answer? Young person, they're both the real right answer. They both mean the same thing. The negative means to the west from my picture. Okay? Any questions about that? If you have questions, hopefully your neighbors can help you, because I'm not there. Okay, let's move on. We cross this out because we got displacement from where he started. Next, I need the magnitude of the displacement from where he started. So magnitude means size. If you look at this, negative 4. If I just want the size, just how far I went, it's 4. Well, that's the absolute value of negative 4. That gives you a hint for how I'm going to draw the symbol for magnitude of displacement. So this is displacement, again, just like before, and the magnitude of the displacement is going to be the absolute value of that. So the magnitude of the displacement, the symbol I'm going to use for that is the absolute value of the displacement, and that's going to be equal to 4 meters. I've taken off the direction information, which is the negative or the west. That's gone. Because the length of this is just 4. 1, 2, 3, 4. So now I've taken care of the magnitude of the displacement from where he started. Let's do these last two, because they're a little trickier. I'll use a different color pen. Next, I need to find his displacement from the origin. So the symbol for displacement is my little arrow here. And now it's not traveled, it's from origin. So I'm going to write O-R-I-G, not the whole word, but just O-R-I-G to make sure that it's a little different. What is my displacement from the origin? So that would mean from the origin to my endpoint in a straight line. How far would it be? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'm 10 away. And in what direction am I away? So I'm 10 meters to the west. Well, west is negative, so I could also write it this way. Negative 10 meters. So So these are the two ways that I could write this. That takes care of my displacement from the origin. And finally, the magnitude of my displacement from the origin. Well, the magnitude would be the length of this arrow and not the direction, the length of the red arrow and not the direction, and the length is 10 meters. So the symbol I'm going to use for that is the absolute value. So this is the magnitude of the displacement from the origin, and that's going to be equal to 10 meters. Okay, let's move on. Big idea number 5. Angles can be measured from any of the cardinal directions. I'm going to do a couple examples here. Describe each of the following angles two ways. So I'm going to draw the angle in first. I'm going to draw something like this. Let's call this a 30-degree angle. There are many ways we could describe this angle, but in physics, we generally just describe this angle in terms of the two cardinal directions that are closest. So we have north, we have south, we have east, and we have west. What is closest to this line is north and east. So we're going to be able to describe this angle in terms of east and in terms of north. To be clear, when you're going straight north with no angle at all, that is called due north, D-U-E, due north. So this would be due north, and this would be due east. And I want to talk about this angle in terms of due north or due east. For practice, I am going to write these two options out in their full glory, and then next time we do it, I'm going to show you some shorthand so you don't have to write out sentences that are quite as long. But for this first one, we'll do it the long way. This angle is north of east. So this is due east, and I'm going north in the north direction from due east. So one way I could describe this angle is by saying it's 30 degrees north of due east. However, north and east are exactly 90 degrees away from each other. They make a right angle. And 90 minus 30 is 60. So I could describe this line as being 60 degrees away from north. Well, what direction away from due north would I have to go? Do I go to the west of due north to make this angle, or do I go to the east of due north to make this angle? Well, that's pretty obvious now that I've said it that way. I'm going to go 60 degrees to the east of due north. So, or 60 degrees to the east of due north. These are the two answers you could give. They are both right. One of them is not righter than the other. They are equally correct. Let's do another one. Let's say I had an angle that went off like this, except it's not drawn to scale, of course. And this was 80 degrees. So there are two ways I can describe this 80-degree angle. I could say that it, compared to due east, it's 80 degrees to the north of due east. So I could say 80 degrees north of, I'm sorry, not east. I said that wrong. This is west. So this is west. So 80 degrees north of west. I apologize, that was probably confusing. So this is due west, and I'm going 80 degrees to the north of due west. That's one way I could write it. Or this one, since 90 minus 80 is 10, then this would be 10 degrees, and it would be to the east of due north. So 10 degrees east of north. All right, let's move on. Let's try one down here in this quadrant. Let's say that we went off at a really funky angle down here. Let's say this is 25 degrees. So 25 and 75 is going to give me 90, so this one would be 75. So this one would be compared with due west. So this is due west here, and I'm coming down 25 degrees from due west. So the first thing I would say is it's 25 degrees in the south direction from due west. So 25 degrees south of due west. South of west, because this is west and I'm going south from it. You guys see this is west and I'm going south from it by 25 degrees. So it's 25 degrees south of west. Or, now this one down here is 75. So this is due south and I'm going to be going to the west of south by 75 degrees. So it'd be 75 degrees west of south. Okay, let's do one in the remaining quadrant. Let's say I came off along here like this, and this is a 40-degree angle. You should be getting pretty good at these by now. So from due east, I'm going to be going south by 40 degrees. So it's going to be 40 degrees south of due east. Or, so 90 minus 40 is 50. So if I were to go straight south, it would be 50 degrees to the east of due south. So 50 degrees east of south. Hopefully that practice helped for those of you that were not in Boy Scouts or Girl Scouts and did not learn this already. And based on the hands I saw in class the other day, only 2 or 3 of you in each class know how to do this. So hopefully this helps. Example number 3. I'm going to modify number 27 from your AP1 physics textbook. If you want to go ahead and open up your book right now, so you should have your book at your desk. Go ahead and open it up, and we'll take a look at this. You already did this one for homework, but I'm changing it up a little. It's on page 25. So if you look on page 25 of your textbook, it says a city has streets laid out in a square grid, with each block 135 meters long. If you drive due north for 3 blocks, so I'm going to start drawing now. I'm going to, first of all, orient the reader. I'm going to make this be north and positive. I'm going to make this be east and positive. So I believe it says you draw, let's see, you start here and you draw due north for 3 blocks. So I went north for 3 blocks, and each block was 135 meters. So this distance here is going to be 135 meters times 3. And I did it in my calculator, and I got 405 meters. And then you go let me just double check, west for 2 blocks. So west is this direction, so I'm going to go west for 2 blocks. Somewhere along in here. So then it's going to be 135 again. meters, 135 meters times 2. When I did that in my calculator, I got 270 meters. Okay. I am going to modify this problem, and I'm going to ask you to look for distance, displacement, and the magnitude of the displacement. So if you look in the book, it only asks how far you are from your starting point. How far you are from your starting point would be your distance. No, it's not. Sorry, it would be the magnitude of your displacement. How far you are from your starting point is the size of your displacement. So how far you are from your starting point would be if you drew a straight line from where you start to where you end. So I need to look for distance traveled. I need to look for the displacement, and I need to look for the magnitude of the displacement. I'm going to just point out right now that, like I just said a minute ago, my displacement is going to be like this, and I'm going to be able to measure that displacement either from here or from here. Those are the two, because I have my cardinal direction north here and I have my cardinal direction west here. This angle can either be measured from with respect to north or from or with respect to west. Those are two ways I can measure that displacement. Before we move further, I'm going to write a little note up here. Please check your calculator's mode. There's a button on your calculator that says MODE if you have a Texas Instrument. If you have a Casio, I have no idea how you find it, but you find it some kind of way. You need to check your mode and make sure that your calculator's mode is in degrees, not radians. Go ahead and do that now. If you need help from your neighbor, get the help. If the sub needs to stop this video for a second while you do it, go ahead and stop it and restart it once everybody has their calculators in degrees. All right, moving forward, let's find the distance. The distance traveled. Well, if I went 405 here and 270 here, then my distance traveled must be equal to 405 meters plus 270 meters. So my distance must be equal to 675 meters. And that is the answer to my distance question. That's the distance traveled. That's pretty easy. Now let's move on to the magnitude of the displacement. So the magnitude of the displacement is the next easiest one to do. So this is the symbol for magnitude of the displacement. We don't know what it is, just like we didn't know what D was here. This is a right triangle because due north makes 90-degree angles with due east. Due north, due east. Well, there's an old dead guy from Greece named Pythagoras, and he told us something interesting. He said that anytime you have a right triangle, that two of the legs have a relationship with the hypotenuse. The hypotenuse is the bit that is on the opposite side from the right angle. The hypotenuse, according to the way you've probably learned it in school, is always going to be C. So C is always the hypotenuse. It's located on the opposite side from the right angle. The other two legs are called A and B. But a lot of you always ask, Mr. Williams, which one's A, which one's B? It does not matter. It doesn't matter. It doesn't make the slightest difference. This one could be A, that one could be B. Or this one could be B, and that one could be A. It doesn't matter at all. All that matters is C is the hypotenuse, and then the other two are A and B. Okay? So Pythagoras' theorem says that C squared is equal to A squared plus B squared. And I want to know the length of C. So I don't want to actually know C squared. I want to know C, so I'm going to need to take the square root of both sides. So C is equal to the square root of A squared plus B squared. In this case, A, I don't know, let's call A this one. So 405 meters. And this is 270 meters. I'm trying to be careful here with you. I put the 405 meters in parentheses and the 270 meters in parentheses because otherwise kids will forget to square the meters as well as the number. Okay, so you do the math and you should get 454.8 meters. And that is the magnitude of the displacement. I'm going to put a box around it because I have found my answer. And I'm going to cross it out here because I've solved it. Now that I know the magnitude of the displacement, the only thing left is to find the angle and then talk about the angle at the same time I talk about the magnitude. And that'll give me the displacement. So let's go ahead and do that. I'm going to draw a line here. So if we call this angle theta, and we don't know it, so equals question mark. The tangent, we know, so if this is theta, and this is opposite side, and this is adjacent side, see, this is opposite for my angle, this is adjacent to my angle, then tangent is the right trigonometric identity to use, because tangent deals with opposite and adjacent are the two bits that I know. So tangent of theta is going to be equal to opposite over adjacent. But I do not want to know tangent theta. I want to know theta. So if I take tan inverse of both sides, this will lead to theta is equal to tan inverse of the opposite divided by the adjacent. In this particular case, that is going to be tan inverse of 270 meters divided by 405 meters. The meters cancel because you have a meter on the top and the bottom, so those units are gone. And theta is going to be equal to 33.7 degrees. That means that this angle here is not unknown anymore. Now it's 33.7 degrees. Well, if this is 33.7 and this is due north and this is due west, well, north and west make a 90-degree angle with each other. And 90 minus 33.7 is going to be 32.8. That doesn't seem right. That ain't right. Hold on a second. I kind of messed up my numbers, I think. Let me just double check and see if I screwed up. So tan inverse of 270 divided by 405. So that's 33.6. Yeah, that's right. No, that's 33.69. I'll round that to 70. Okay, so that's good. Minus 90. That's 56.3. Okay, that makes me feel better about life. I apologize. That's 56. So if this is 33.7, this should be 56.3 degrees. There we go. I thought I prepared for this, but clearly I messed up. So now let's report out. This angle here is going to have a magnitude and a direction. So I'm going to have two options for my displacement. It's going to be equal to 454.8 meters at 33.7 degrees. So there's due north. It's going to be to the west of north, or it's going to be 454.8 meters at, what did I say that was? Oh, there it is, 56.3. 56.3 degrees. Now, due west is going to be north of due west. So these are my two answers that are possible for the displacement. Both of them are correct. Neither of them is more correct than the other. All right, let's move on. Now we're going to move to number 28 of your book. Number 28 says that there is a butterfly. It is sitting in the top of a tree in the center of a garden, and it's going to fly from the top of the tree down to a red flower on the garden's edge. It doesn't tell you whether it's on the left or the right, and that's going to be a problem. But that's okay, we'll do it. The garden is 12 meters wide, and I'm going to change this problem up, and we're going to look for the distance the butterfly goes, the displacement of the butterfly, and the magnitude of the butterfly's displacement. So let me draw my picture here. We don't really say east or west or left or right. So we've got up, and I'm going to make that positive. And down, we're going to call negative. And then I'm going to call this direction, this away, positive. So I'm going to draw my picture, and then we'll have a better way of looking at things. So here's my tree. I can't draw butterfly, kids, so I'm just going to draw some ridiculous bird. This is my bird. That's my butterfly. I am not an artist, so that's about as good as she gets right there. And here's my garden, and I can't draw a flower either, so we'll just here we go, flower. Yeah, that's a flower. That's what I'm talking about. So here is our bird, and that's our flower. And we are flying right along this path right here. That's where we're going. The problem says that our garden is 12 meters. All right. It also tells us that it's 8 meters down from the top of the flower straight down from the bird. So this here, that's 8 meters. And it tells us it's 6 meters. Well, you're halfway. So then this here's got to be 6 meters because it's half the garden width. So this is 6 meters. Okay. Well, I'm feeling better about life already because now I know that this is a right triangle. Got to be. Straight down is going to be perpendicular to straight across. So we got a right triangle. I love right triangles. They let us use Pythagoras' theorem. That makes a lot of stuff work around here. I asked you to find the distance that butterfly traveled and the magnitude of the displacement. If you just look at the picture, you can tell already that if that butterfly flew in a straight line, like it said in the problem, that the distance it traveled is going to be the same as the magnitude of its displacement. Because we're not adding up 6 and 4 to find distance now. The butterfly didn't fly down and then fly across. The butterfly flew straight over here, straight in this line. He flew along the hypotenuse. A lot of kids mess that up. So that's why I'm making a big deal out of it. I'm going to write that down. In this case, the distance traveled is the same as the magnitude of the displacement. And you can tell that pretty easily just from the picture. It's a right triangle. Which sides are A, B, and C? Well, this here is C, and you choose which one's A or B. I couldn't care less. So according to the Pythagorean theorem and Pythagoras' ideas, C is going to be equal to the square root of A squared plus B squared, and we'll call it 8 meters squared plus 6 meters squared. And when you plug that in your calculator, you should get 10 meters. So 10 meters is the length of this. And this bird is going down this way. So I'm going to draw an arrow in here like this so you know. Therefore, my distance traveled is equal to 10 meters. And that is my first one answered. I'm going to cross it off here. The next easiest one is the magnitude of the displacement. Well, that's the same darn thing. So the magnitude of the displacement is also 10 meters. Well, great. Look at me. I've answered 2 of them. I haven't hardly done anything. Now the toughie. Well, not that tough. We're getting better at this. So this is a right triangle, and I'm interested. What angle am I interested in? Well, that's a really good question, Mr. Williams. What angle are you interested in? Well, the butterfly starts up here, so I'm interested in this angle, or I'm interested in this angle. All right. So this angle right here, what would that be? Well, if I can find this one, I can take 90 and get that one. So we'll go with this one first. So tangent of theta is equal to opposite over adjacent. So theta must be equal to tan inverse of opposite will be 6 meters over 8 meters. And when you plug that in, I got 36.9 degrees. So if this is 36.9 degrees, then this one up here must be 53.1 degrees. So then there are 2 answers for my displacement. One of them will be 10 meters at 36.9 degrees, and that 36.9 is towards the flower from the vertical line. So I'll write that out. Towards the flower from the vertical. Or it can be 10 meters at 53.1 degrees. Now, 53.1 degrees would be down from the horizontal. So it would be below the horizontal towards the flower. Below the horizontal towards the flower. And that would be the answer for that one. I hope these examples have been useful for you. That concludes the video that I have for you today. And I will have another video for you tomorrow. There is a homework assignment on the whiteboard at the back of the room. Please do it tonight. Thank you. Have a great day.